Okay, welcome back. We have reached section 4.6.3. And in fact, 4.6 is the last section that we will be doing in chapter 4. So we are not going to do section 4.7. And the basis of section 4.6.3 is the Levy characterization of Brownian motion. And the main theorem there is theorem 4.6.4. We do a Levy characterization of Brownian motion in one dimension, and later we do it in multiple dimensions. And in fact, this is a very nice result. So it gives another way to check that a process is a martingale. And it also is very helpful to proving very nice theorems that we will be encountering in chapter number 5. So we start in dimension 1, which is indeed theorem 4.6.4, the 1D version of the Levy characterization. And the basis is as follows. Let MT, T greater equal to 0, let that be a martingale with respect to the filtration script FT, T greater equal to 0. Now assume that M0 is equal to 0 and assume that MT, T greater equal to 0 has continuous paths, and moreover assume that the quadratic variation of M is equal to T, T greater equal to 0. So it has quadratic variation T, just like in the case of a Brownian motion. Then the theorem says that MT, T greater equal to 0 is a Brownian motion. So the conclusion is, when we assume M0 equals 0, continuous paths and a quadratic variation of T, then MT must be a Brownian motion. Now, if you look carefully at what we are saying here, is that the property that MT is a martingale plus the property that the quadratic variation equals T is in fact enough to determine the distribution. That is to say, what we are lacking next to continuous paths and M0 equals 0 is that the increments are independent and normally distributed with mean 0 and variance equal to the size of the time interval. So the variance of MT minus MS, S less than T, is equal to T minus S. So that is lacking here as compared to the usual definition of Brownian motion. But it's really equivalent. If you go through the derivation that we have done, this information, the independence and the mean 0 and variance T minus S, normally distributed, that comes from the fact that the quadratic variation of a Brownian motion is T. So if you couple the quadratic variation being T with MT being a martingale, we can prove that we are dealing with a Brownian motion. So essentially, it's enough to determine the distribution of the increments and to show that they are independent. Yeah. So if we prove this, what we need to do is we need to show that in a time partition, T1 less than T2 less than T3 up to Tn, we need to show that MTi plus 1 minus MTi, when I runs from 1 to n minus 1, that these increments are independent and that are normally distributed with mean 0 and variance Ti plus 1 minus Ti. That is what we need to show. And how are we going to do that? Well, we are going to do that by means of the moment generating function. And we have also seen in earlier lectures that the moment generating function is decisive for these type of statements. So it's enough to show, in fact, that in expectation, the expectation of e to the u1 m t1 plus u2 m t2 minus mt1 plus etc. to un mtn minus mtn minus 1, that is equal to the product of the individual expectation, the expectation of e to the power u1 mt1, and that is of course mt1 minus mt0, but because mt0 is equal to 0, that one is not written down, times up until expectation of e to the power un mtn minus mtn minus 1. And then we have to show that this is indeed equal to e to the power 1/2 u1 square t1 times e to the power 1/2 u2 square t2 minus t1 times etc. times e to the power 1/2 un square tn minus 1. So the first step here is the independence of the terms, and the second step here is the normal distribution of the individual terms. Yeah. So we want to prove this statement. We need to prove that MT has a normal distribution. If one holds, we have in fact proved what we want. Yeah. And we will extend what we did earlier to this situation. Now, the book is short about this proof. Yeah, the book only proves that MT is normally distributed with mean 0 and variance t. And it does that by showing that for any t, this expectation, e to the power, the expected value of e to the power u mt is e to the power 1/2 u squared t. And equivalently, if we divide left and right hand side by this right hand side, and this is a deterministic term, so we can take it under the expectation sign, this is equivalently equal to the expectation of e to the power u mt minus 1/2 u squared t, that expectation being equal to 1. Again, if we divide left and right hand side by this term, we end up with 1 here, and we end up with this term here. Now, in fact, with W replacing M here, this is what we call a geometric Brownian motion. And we have showed in a previous lecture that this is in fact a martingale. So all the expectations are equal to the expectation with t equals 0 then, and with t equals 0, W0 is 0, and here substituting 0, we get e to the 0, and that is equal to 1. So if we are able to show that e to the power umt minus 1/2 u squared t, when that is a martingale, then we have proven our statement. Now, we have shown this in the past with wt instead of mt, by showing that the expression in the expectation operator is in fact an Ito process. So we have applied the Ito-Diplin formula. And now with MT instead of WT, we will do the same. Yeah. And if we think again of what we have done before, when we derived the notion of stochastic integral, there were essentially three properties of a Brownian motion that we have used. And we have never used the fact that the Brownian motion had a normal distribution. And the only time we really used that fact was in the theorem where we showed that with the adapted so-called deterministic process, delta, as the integrand, that the Ito integral then had a normal distribution. That's where we used that WT was a Brownian motion. But the other essential properties in the derivation of the integral were used for all the other aspects. So let's recap. We have seen this form when MT was equal to a Brownian motion, WT. And there we did the derivation. So what we need to show essentially is that e to the power u mt minus 1/2 u squared t is a martingale. Yeah, if we are able to show that, we have shown that this expectation is equal to 1. So we will first prove this and then prove this equation 1. And recall that equation 1 was in fact the one with on the basis of the time partition. Now note that the expression we are dealing with under the expectation sign e to the u mt minus 1/2 u squared t, it resembles a Brownian motion, but the Brownian motion wt is replaced by the martingale mt. So again, in order to show that we're dealing with an Ito process, that we're dealing with an Ito integral, of which we know that it is a martingale and it has mean 0, we show this with the help of Ito Diplin. One is tempted to use Ito Diplin's formula, and then it makes sense to choose f of t and x being e to the power ux minus 1/2 u squared times t, and we substitute for x mt. That makes sense, and we will do that indeed. So the three properties that we have used to define the Ito integral, as I mentioned, we did not really use the fact that Brownian motion as independent increments was normally distributed with mean 0 and variance t minus s. But the things that we have used are the continuous paths, the quadratic variation of w being equal to t, and the martingale property, leading to the fact that the integral that we define is a martingale. And these three we also have in our theorem 4.6.4. So we keep them in this part. So it makes sense that we repeat the construction of the Ito integral, but now with respect to the martingale mt, t greater equal to 0. And then satisfying the properties 1, 2, and 3 that are in fact the assumptions in our theorem. So we do that in a similar way. So we will derive in a similar way the notion of an Ito integral, and we will show that the integral from 0 to t delta t dmt with respect to a martingale is a martingale, right? So the resulting Ito integral, we want to show that it is an Ito integral. And then the resulting Ito integral, the integral from 0 to t delta u dmu, is a martingale, and therefore in expectation it is equal to 0. That is the definition of the martingale. So again, so when we substitute small t equals 0, then we get expectation 0. And that is one of the properties that one can deduce from the fact that an Ito integral is a martingale. So we will use the extended Ito Diplin formula to this situation, and we will do it exactly as we plan. So remember the aim of this is to show that in expectation e to the u mt minus 1/2 u squared t is equal to 1. Yeah. And what we do is we apply the extended Ito Diplin formula, and our f of t and x is written like e to the ux minus 1/2 u squared t. Now ft of t and x is equal to minus 1/2 u squared times the term itself times f of t and x. Fx of t and x, the derivative with respect to x, that is u times f of t and x. And the second derivative, fxx of t and x, that is then u squared times f of t and x. We write them down here, you see them, and we write them down on the next slide, and we will work with them. So again, ft, it's written out here, and it's minus 1/2 u squared of f. Fx is u times f, and fxx is u squared times f. These three, just wrote them down on the previous slide. Here they are repeated for convenience, and then we will apply the extended Ito Diplin formula, and we apply it to e to the power u mt minus 1/2 u squared t. We call that our f. For x, we substitute mt. And then this Ito Diplin's formula says this is equal to f at 0 m0 plus 1/2 the integral from 0 to t of df dt, and minus 1/2 u squared times f ds, where f is evaluated at sms, plus the integral from 0 to t u times f dm, df dx times dm, plus 1/2 the second derivative, the integral from 0 to t u squared times f dms dms. Well, dms, we also know that is equal to dt, right? Remember one of the assumptions here in our theorem. And if we then look carefully, we see that this one with minus 1/2 u squared f ds cancels out with this one plus 1/2 u squared f dt ds. So they cancel out, and what remains is f at 0. Well, f at 0, replacing, substituting 0 for t here gives us a 1. E to the 0 is equal to 1. So what remains is that e to the umt minus 1/2 u squared t is in fact, and that was our f, it is 1 plus the integral from 0 to t uf dm. And that is an Ito integral with respect to the martingale m. Yeah. So the right-hand side here contains the Ito integral and hence is a martingale. Yeah. This Ito integral, this is a martingale. So taking the expectation of the left and right-hand side, the expectation of the left-hand side is here. A constant is just a constant, plus the expectation of the Ito integral, which is equal to 0. So in total, this is equal to 1. And that is exactly what we wanted to achieve, right? The expected value of e to the power umt minus 1/2 u squared t, that is equal to 1, as required. So what we have now shown is that e to the power umt minus 1/2 u squared t is a martingale, with m here, is a martingale. And also, so mt is distributed like a normal distribution with mean 0 and variance t. Now we need some work to get back to this equation 1. So if we know it's a martingale, so when s is less than t, we know by the definition of the martingale that if the filtration is up to time s, then the conditional expectation of e to the umt minus 1/2 u squared t, given the filtration up to time s, that is in fact e to the ums minus 1/2 u squared times s, by the definition of the martingale, by the martingale property. This holds true. Now we can rewrite this a little bit by means of iterated conditioning. And we do that as follows, right? First of all, what we will do is we can, so let's go back one piece. We can divide by e to the ums. So e to the ums, we can take it to the left-hand side. And moreover, we can take it under the expectation sign because we have the filtration up to time s. This is, in that case, that is a known part. So we can also take it under the expectation sign. And this little part, we can move it to the right-hand side. As a result, we get that in expectation, e to the power umt minus ms, given a filtration up to time s, is e to the power 1/2 u squared t minus s. Now we do a trick, a little technique, and that is we do iterated conditioning. Yeah, we know that if we take the expectation of both sides, of course, the right side taking the expectation of the deterministic function just gives us the deterministic function. But if we take the expectation then here, from iterated conditioning, we know that the expectation of the conditional expectation is just the expectation of the term inside, right? So this is nothing but the expected value of e to the power u mt minus ms. And these terms we will encounter when we are dealing with equation 1. And what this essentially says, if we look at the left side and the complete right side, is that mt minus ms is distributed normally with mean 0 and variance t minus s. Now, let's look at our partitioned function. Let's look at the partitioning 0 less than t1 less than t2 up to tn. And let's reconsider the moment generating function on this partition, the expected value of e to the power u1 mt1 plus u2 mt2 minus mt1 plus etc. un mtn minus mtn minus 1. And we will repeat that little trick that we did over here. We repeat that iterated conditioning that we did over here in order to get to these type of forms, right? This is what we know. This is what we have. If we do some iterated, this is identical to the iterated conditioning. So we take some term inside, and then we can make use of the fact that we know what it is. So we do that, and we do the iterated conditioning. We take the iterated conditioning, and we take the filtration up to tn minus 1 here, tn minus 1. Then by take out what you know, all these parts here can be taken out. And they are all known. With a filtration ftn minus 1, they can be taken out. This one can also be taken out, but we keep it in. So what remains under the expectation sign is e to the power un mtn minus mtn minus 1. Now that is the one for which we had our expression. So here we can substitute the expression that we have just found, and that is e to the power 1/2 un squared tn minus 1. And the other part just remains under the expectation sign. Now we repeat that, and we will take the expectation, again, iterated conditioning with respect to tn minus 2. And then tn minus 3, etc. We go back one step by time step, we go back. And in the end, what remains is a product e to the power 1/2 u1 squared t1 times e to the power 1/2 u2 squared t2 minus t1 multiplied up until e to the power 1/2 un squared times tn minus 1. And that is then done indeed with the iterated conditioning like we saw in the previous slide. And that concludes our proof, right? If we, by doing this, by showing this, we have shown that mt1, in fact, mt1 minus mt0, but mt0 is equal to 0, up until mtn minus mtn minus 1. These are all independent, normally distributed increments. So mti plus 1 minus mti is normally distributed with mean 0 and variance ti plus 1 minus ti. Exactly what we wanted to show. All right, theorem 4.6.5 is a generalization to 2 dimensions. So that's the Levy characterization of Brownian motion in 2 dimensions. And that essentially goes very similar, the generalization goes very similar to all the proofs we have seen in the 1D case. Still, it's interesting because it gives us an interesting result in the end, and it gives us an interesting finding. And also, as you can imagine, we will use a multidimensional Ito-Diplin formula. It is important and interesting to see how that goes. So in the multidimensional, in the 2-dimensional case, let's have m1t, t greater equal to 0, and m2t, t greater equal to 0. Let them be 2 martingales related to the filtration ft, t greater equal to 0. And then, as you can imagine, we generalize the assumptions from 1D to 2D. So we will assume m1 0 is equal to m2 0 is equal to 0. We assume that m1t and m2t have continuous paths, and the quadratic variation of m1 is equal to the quadratic variation of m2 is equal to t, and the cross variation of m1 and m2 is equal to 0. That is the assumption for this, and if we have this, then the vector m1t, m2t, t greater equal to 0 is, so these m1t and m2t, they are independent Brownian motions. In other words, it's a two-dimensional Brownian motion. Now the sketch of the proof, again, it goes very similarly to the 1D case, so we will sketch it here, and only the essential ingredient with the generalized multidimensional Ito-Diplin formula we will do in some detail. So by Levy's characterization in dimension 1, we see that m1t, t greater equal to 0, and m2t, t greater equal to 0, these are Brownian motions. Yeah. So what remains is to prove that they are in fact independent. And we can do that by showing that their joint moment generating function is equal to the following. So in expectation, e to the little u1 m1t plus little u2 m2t, the expectation of this expression must then be equal to e to the power 1/2 u1 squared t plus 1/2 u2 squared t. Or equivalently, dividing by the right-hand side, we end up with, again, our expression, the expected value of e to the power u1 m1 plus u2 m2 minus 1/2 u1 squared plus u2 squared times t. The expected value of this expression should be equal to 1. And here we see a two-dimensional form. We recognize an x here, a y here, and a t here. So we see that we will be doing the multidimensional Ito-Diplin formula with x, t, x, and y, essentially, right? So we can show that by using the extended Ito-Diplin formula, f of t, x, and y is in this case e to the power u1x plus u2y minus 1/2 u1 squared plus u2 squared times t. And then the first derivative with respect to t is minus 1/2 u1 squared plus u2 squared times f. The first derivative with respect to x is equal to u1 times f. And the first derivative with respect to y is u2 times f. The second derivative with respect to x is u1 squared times f, and the second derivative with respect to y is u2 squared times f. Well, the mixed derivative, we don't really need it. So the mixed derivative fxy is not needed because from our assumptions dm1, dm2 is equal to 0, and the cross variation was assumed to be equal to 0, it follows from the assumption that the cross variation is equal to 0. So that one need not be written down in our extended Ito-Diplin formula. All right, this is our f. For x, we substitute m1. For y, we substitute m2. And then this is nothing but the f 0, m1, 0, m2, 0, and that is again equal to 1, right? Substitute 0 here, here, and here. It's e to the 0, that's 1. And then this term is the integral from 0 to t, df dt times ds. df dx times dx, dm1, u1f, evaluate s, m1s, m2s, dm1s, and with respect to y, the integral from 0 to t, u2f times dm2, and the second derivatives plus 1/2, the integral from 0 to t, u1 squared f times dm1 dm1, and dm1 is equal to dt, plus 1/2 integral from 0 to t, u2 squared f times dm2, that is equal to dt. And here we see that some terms will cancel out. We see that we have here minus 1/2 u1 squared f ds, and here we have plus 1/2 u1 squared f ds. And here we have minus 1/2 u2 squared f ds, and here we have plus 1/2 integral from 0 to t u2 squared f ds. So these cancel out, and what remains is, in fact, that e to the power u1 m1 plus u2 m2 minus 1/2 u1 squared plus u2 squared times t is equal to 1 plus the integral from 0 to t u1 f dm1 plus the integral from 0 to t u2 f dm2. These are two Ito integrals with respect to the martingale. The Ito integrals are martingales, and therefore in expectation they will be equal to 0. So what remains is the Ito integrals are martingales, their expectation is equal to 0. So what we have is indeed what we were looking for, the expectation of e to the power u1 m1t plus u2 m2t minus 1/2 u1 squared plus u2 squared times t is equal to 1. That is the form that we were looking for, and it tells us essentially that m1 and m2 are independent, and that was exactly the notion we were looking for on the basis of these moment generating functions. Now let's have a nice example. Let Wt be a vector valued Brownian motion, W1t, W2t, a two-dimensional Brownian motion. And so by definition, W1 and W2t are independent. And now let's consider the price process, and now two-dimensional price process. So stock price process, we have seen it previously, stock price process, geometric Brownian motion. For S1, stock 1, if you wish, ds1t is alpha 1 s1t dt plus sigma 1 s1t dw1t. And now let's look at a second stock price process, which has a little bit different Brownian motion. So that is ds2t is alpha 2 s2t dt plus sigma 2 s2t times rho dw1t plus the square root of 1 minus rho squared dw2t. So what we see here is, here we see the drift term, the growth rate of the stock. Here we see the uncertainty, volatility of the first stock, volatility of the second stock, sigma 1, sigma 2, and we see a correlation, in fact, a correlation, or a parameter rho, a correlation coefficient, which is between -1 and 1. These are all constants. Now let's analyze that process S2t, t greater equal to 0. Yeah, and the first thing we do is let's look at this term behind S2, and let's call that W3. Yeah, let's call that a Brownian motion, W3. And you may remember this, that we can do this, and we call it W3. It is equal to rho dw1t plus the square root of 1 minus rho squared dw2t. And then W3t, t greater equal to 0, is a martingale with W3 0 equal to 0, right? We see W1 0, W2 0, and moreover dw3t, dw3t. If we multiply this by itself, so we get the first one squared, so that's rho squared w dw1t, dw1t is dt, So that is the first term, and the mixed term will disappear because these are independent, as you recall. And then the second one gives us the square root of 1 minus rho squared gives us 1 minus rho squared, and dw2t, dw2t gives us dt. So in total, dw3t times dw3t gives us dt. Now, by Levy's characterization in one dimension, we see that W3t, t greater equal to 0, is a Brownian motion. And therefore, we can write S2t, S2t, t greater equal to 0, we can write it with the W3t. ds2t is alpha 2 S2t dt plus sigma 2 S2t dw3t. And this is the familiar form, of course. So this is a geometric Brownian motion. You remember, with S2 here and S2 here, a drift term here and a volatility term here, and time increment here, and a Brownian increment here. That was the form of the geometric Brownian motion. And the solution of this was S2t is S20 times e to the power sigma 2 W3t plus alpha 2 minus 1/2 sigma 2 squared times t. Now let's look at the correlation. Let's try to find the correlation between W1 and W3. How do we do that? Well, we do that with the Ito product rule from the last lecture. Yeah. And the Ito product rule told us that the change d W1t, W3t would be the usual product rule, W1 dW3 plus W3 dW1 plus that quadratic of that cross variation here, dW1t dW3t. Now let's substitute for W3 and for dW3, let's substitute its definition. Yeah, so let's write out W3t in this expression. And then, well, the first thing we do is this is W1t dW3t plus W3t dW1t. And then here, this, in fact, this is a term. You remember this is a term. Here we can write out W3. So this is a term with W1 and a term with W2. W1 and W2 are independent Brownian motions, so only the W1 term remains. So what we end up here is rho dt. And in integral form, this looks like this. W1t, W3t is W10, W30 plus the integral from 0 to t, W1t dW3t plus the integral from 0 to t, W3t dW1t plus rho t. Now here we again recognize Ito integrals with mean 0, right? Martingales with mean 0. And therefore in expectation, taking the expectation in the left and right hand side, we find that the expectation of W1t, W3t is rho t. That is in fact the correlation between W1 and W3. So in fact, we have made a form in which S1 and S2 are correlated, and they are correlated via the Brownian motions, so W1 and W3. So that formulation gives us a formulation in which S1 and S2 are correlated. And that concludes today's talk. I thank you for your attention.